selecting a motor, you really want to know the torque and the RPMs. Decrease the speed by a ratio of 10 to 1, the torque also goes up by 10 to 1. Open loop is where there is no encoder feeding back to your controller the position. If you're going to run this thing 24/7 and you want to run it at some optimal speed, then a VFD on the AC motor is a much better choice. All of the different motor technologies have a different cost associated with them, and there's usually a two-part cost. There's the cost of the motor and the cost of the control. Now in the case of like an AC motor that's running at a constant speed, you're talking a contactor, which simply turns the power on and off to the motor. And that's relatively inexpensive, and again, that's real common in like conveyors and that type of thing. Now, if you need to reverse the motor, now you're into a different kind of contactor that can do reversing. And that's doable too, but that contactor's a lot more cost. Then, if you're using a DC motor, reversing is very easy. So again, the question comes down, do I need to reverse? Can I run in one direction all the time, or do I need to sometimes run in the opposite direction? So this is another factor that you have to take into account. Then there's the actual speed that you need, and that's determined by the process that you're trying to, whatever it is you're trying to move. That comes directly from that. And so you can do variable speed motors with gear reducers, and you can do them with direct drive. So sometimes you're going to want to choose another type of motor. And that comes in when you start talking about positioning. Because if you want to position a load, now you have to have control of the start and stop to some degree, and some degree of accuracy. So in case of, like, again, back to the conveyors, a common way to do this is with nothing more than a sensor that senses a package, say, moving on the conveyor, and that when you break the beam on that, it comes to a halt. Now, that's one way of positioning, and it's quite common to do it that way. And then the other is, well, I want to position to some numerical value. I'd like to tell it to go 10 inches or 10 feet and stop. So, and also you may want to move between positions. So I want to move to 10 inches and then I want to move to 10 feet with the same load. So now, in order to do that, you have a couple of choices to make. One is you can add an encoder to the motor, and an encoder can be added literally to any motor. And the encoder gives you position feedback as a function of revolutions of the motor. So if the motor, you might have an encoder that's 1,000 counts, which means that you can detect position down to 1,000th of the revolution of the motor. So encoders give you a way to do that. Now, there's another way to do it, and this is quite common in inexpensive products and sometimes in very expensive products, but a stepper motor. A stepper motor is a true digital motor. You send it a step and it moves one step. If you send it a different way, it can move back one step. So it can move forward and back. And they can be run what they call open loop. Open loop is where there is no encoder feeding back to your controller the position. Instead, your controller is simply tracking how many steps it sends to the stepper motor. And that's called open loop. As long as the motor is not ever overloaded, that can give you very good position accuracy, even over long periods of time. Right? Now, an advantage to stepper motors is that they have very high torque at very low speeds. Whereas other kinds of motors, like servo, which would be used for positioning, they tend to have higher torque at highest speeds. So where one, the torque is falling off as the speed goes up, the other one, the torque is increasing as the speed goes up. So if you want to run something very slow, and when I say very slow, down like 1 RPM and so forth, if you have enough torque, you might get away with using a stepper. And the stepper, now steppers can also run in open loop speed. In other words, you don't care where the position is, you're just going to send it a pulse train that tells it to run at a constant speed. And the speed will be very, very constant. And they can hold, they're very good at holding a steady speed. So that's another way of doing it. With a servo, there's an encoder. It feeds back to the motor and motor controller, and then the controller positions the motor based on what the encoder says. Now, that's called closed loop. And the advantage to closed loop is that if you get out of position for some reason, like an overload condition, the encoder will tell you that you're where you should be. And so you have the ability to correct your position. So that if you need very, very accurate position and you have to be there, you have to be certain that you want to be there, you're looking at using a servo motor. Now, servos can be both AC and DC, because as long as you have the encoder, you really don't care what the power source is. So there are brushed DC servos and there are AC servos that don't have any brushes. But they work from the point of view of selecting the motor, they work the same way. And the primary differences in the brushed versus brushless is cost. The brush motors are cheaper and the brushless motor is more expensive, and also the lifespan. So that comes into another factor with motors. When you're selecting a motor, how long is it going to run? Because there are lots of tasks where the motor runs for seconds at a time and then sits for brief periods or for long periods of time. An example is the electric windows on your car. The electric windows on your car, you push the button, the window opens in a few seconds, and then maybe it doesn't open again all day. So that's an example where you can't justify the cost of a motor that has a huge lifespan because it's never going to be used. A car that's 20 years old probably can get by with a brushed DC motor, and DC is the choice for a car. Why? Because you have a battery and you don't have AC. So all your window motors are typically brushed DC. So that's where the brushed DC comes in. Brushed DC can have a fairly good lifespan. I've used motors where they get several thousand hours before they need brushes, and they're usually brush repair or replacement is a simple thing to do, so it's not uncommon. I used to build a line of machines that did watering in the greenhouse, and they typically ran once or twice a day for half an hour, and so 1,000 hours of life meant that they would go 2,000 times before the motor brushes were wore out. And since it was a 3-month season, it wound up to be quite a few years. In fact, we almost never changed motors. They usually lasted much longer than the lifespan of the machine itself. So that's a good choice. Again, the controls for a DC motor are very inexpensive, and so the combination of controller and motor cost is typically lower still today than the cost of an AC motor and a VFD, a variable frequency drive. So if you need variable speed, but you don't need a really high duty cycle, where you're going to run 24/7, then the DC motors can be a good choice. If you're going to run this thing 24/7, say, a cooling fan in a building and you want to run it at some optimal speed, then a VFD on the AC motor is a much better choice, because there's 8,000 hours in a year. Your brushed motor would wind up needing to be have brushes in it several times in a year, whereas the AC motor has no brushes and no moving parts, so it'll run for years and years. Typically what fails in an AC motor is the bearings, and the bearings can go, I've seen them go 7 years running 24/7 without any problem, and that's what usually fails first. So electrical failures and burnouts and stuff, that doesn't normally happen as a function of wear. That's usually, if a motor burns out, it's a function of overload. So you've done something to overload the motor. And quite often that's something like a failure of a gear motor. The gear motor has worn out and now the load on the motor is going up. So those are the things that we come into contact with as we build automation. And it's always an interesting challenge to select the motors that do what we need to do and keep the cost in place. So on a recent project,